On the morning of May 30th, 2024, Curiosity was on a routine exploration mission, moving carefully across the red dust of Mars. Standard analyses, repetitive soil scans, and a cautious route over the rocky terrain. But sometimes major discoveries don't follow a plan. They happen in silence, after a simple mistake. This time, that's exactly what happened. The rover's front wheel struck one of the rocks on the surface. It wasn't a hard hit, but strong enough to split the rock clean in half. As the camera systems kept recording, the inside of the rock was suddenly exposed. Its outer surface was dull, dark, and ordinary. But inside was a vivid yellow, one that didn't absorb light but sharply reflected it instead. A crystal-like structure shimmered in the dim sunlight. When the images reached Earth, the first response was silence. These crystals weren't just unusually symmetrical, they also didn't belong on Mars. These yellow formations emerging from a dust-covered layer looked so pure and geometric that, for a while, scientists debated whether it was simply an optical illusion. But once the high-resolution images were analyzed, there was no more doubt. Just below the surface was a layer of loose soil, but within the cracked rock, a distinct mineral pattern had been revealed. With sharp edges and a bright, mirror-like reflection, these crystals appeared to have been sealed off, perfectly preserved from external conditions. NASA's official statement used the following comparison. It's like suddenly finding a clear lake while walking through a desert. In a dry, wind-shaped, and elementally limited environment like Mars, the random appearance of such a pure structure is difficult to explain. What's more, the crystals weren't just near the surface. As the fracture extended inward, similar formations continued to appear. This suggested that the structure wasn't superficial, it had likely formed deep inside the rock, shaped over time by a gradual internal process. But the key question remains, what exactly were these yellow crystals? According to laboratory analysis, the material captured by Curiosity was pure, crystallized elemental sulfur. That is, a structure made entirely of sulfur atoms, not combined with any other element or compound. In this pure form, the substance is chemically very rare. On Earth, it only occurs in specific regions under special conditions. It's typically found around volcanic zones, near hot springs, or in environments where hydrothermal systems directly reach the surface. Because the formation of pure sulfur requires high temperatures, concentrated sulfur gases, and a low oxygen-reducing environment. But Mars doesn't offer any of these conditions. There are no known active volcanic systems on the planet. Traces of hydrothermal activity exist only in the distant past, and the atmosphere is composed almost entirely of carbon dioxide. On top of that, oxygen levels on the surface are extremely low. This makes it difficult for sulfur compounds to remain in a stable form. Typically, Mars contains sulfate minerals, structures that form through the presence of water and oxygen and are known for being more stable. But the crystals Curiosity discovered were pure elemental sulfur, an unstable, highly reactive form that usually doesn't survive long without bonding to other elements. What's more, these crystals were unusual, not only in their chemistry but also in their structure. Their brightness, surface texture, and the way they refracted light were different from classical sulfur minerals. That raised new questions, not just about their presence, but about how they had formed in the first place. So where did this impossible material come from? The crystals Curiosity discovered were located in a narrow fissure system known as the Geddes-Valles Channel, situated on the northwestern slopes of Mount Sharp. From orbit, this region doesn't stand out much, but a closer look reveals a complex geological structure. At ground level, a rocky plateau, roughly half the size of a football field, lies at the base of the channel. The orientation of rocks, the slope of the terrain, and the arrangement of mineral layers all suggest that this area has been reshaped over time by different geological processes. But what truly makes this location remarkable is that no spacecraft had ever examined it up close until now. Orbital imagery had shown only general slope and surface brightness variations here. What lay just below the surface, what kinds of mineral formations existed, and which structural features remained hidden, all of it was unknown. Until Curiosity arrived, there had been no direct data on the rock systems in this region. The channel itself is believed to have formed during one of Mars's wetter periods, and it carries signs of ancient surface flow. Stones on the ground are aligned parallel to what appears to be the direction of past liquid movement. This suggests that flowing material once passed through, depositing sediment in minerals over time. Still, how the crystals formed in this environment, or during which specific period, remains unclear. Moreover, this discovery may not carry geological significance alone. Crystalline elemental sulfur is a substance that can also be associated with biological processes. On Earth, sulfur is found not only around volcanoes or in geothermal areas, but also in environments inhabited by certain life forms. In particular, anaerobic, oxygen-free bacteria use sulfates for energy production, and as a result of this process, elemental sulfur is released. These organisms are known as sulfur bacteria and are adapted to extreme conditions that do not require light or oxygen to survive. Therefore, the presence of pure sulfur crystals on Mars may point not only to a geochemical past, but potentially to a biochemical one as well. Of course, this does not constitute direct evidence of life, but sulfur holds a special place among elements associated with biology. That's because some isotopic signatures, which can only be produced by living organisms, may leave behind sulfur compounds. Curiosity's instruments are not sensitive enough to perform such detailed isotopic analyses. However, the structure, growth pattern, and distribution of the crystal make it a promising candidate for future studies of this kind. The site of the discovery, Geddes Vallis, also stands out in this context. As mentioned earlier, this region shows strong signs that liquid water once flowed here. The rounded shapes of the surface rocks, sediment patterns resembling alluvium, and the overall channel structure all indicate that this area once carried an active water system. This suggests that the environment may have once had the chemical conditions necessary to support life. At this point, a similar region on Earth comes to mind: Mammoth Lakes in California. This is an area characterized by intense geothermal activity and structures rich in sulfur. In the hot springs found here, microbial communities have been identified that managed to survive despite the high levels of sulfur. These organisms have adapted their metabolism to produce energy based on sulfur chemistry. And what's particularly interesting is this: some of the crystalline structures found in this area are remarkably similar to the Martian discovery in terms of shape and growth characteristics. Of course, the two environments cannot be directly compared. The current surface conditions of Mars are not suitable for liquid water or active biology. However, this does not mean that such an environment never existed. In fact, layered formations found in Jezero Crater and around Mount Sharp contain signs of ancient lake systems. This raises the possibility that the crystals preserved beneath the surface could be remnants of a much older era. Naturally, conducting such in-depth analyses requires a reliable exploration system that can operate continuously on the surface. And this is precisely where the story of Curiosity, which made this discovery entirely by accident, comes into play. When Curiosity landed on the surface of Mars in 2012, its mission duration was initially planned for just 2 years. But even after 12 years and hundreds of miles of travel, this robot is still operating, transmitting data, and continuing to make new discoveries. Curiosity is a versatile rover at the core of the Mars Science Laboratory mission. Its body is about the size of a car, weighs approximately 2,000 pounds, and carries 17 different cameras, a laser spectrometer, an X-ray analysis device, and even a small onboard laboratory. This system can collect samples from the Martian surface, analyze them, and transmit the results directly back to Earth. In other words, it's not just an observer, it operates much like a scientist. And the working conditions would push the limits of any robotic system. Nighttime temperatures can drop to minus 130 degrees Fahrenheit. The thin atmosphere results in high radiation exposure. Frequent dust storms occur, and low gravity constantly challenges mobility. Yet Curiosity keeps operating thanks to its radioisotope thermoelectric generator. This system converts the heat released by the natural decay of plutonium-238 into electricity, powering its systems and keeping its internal components warm. As a result, it can function continuously, day or night. But this extended mission hasn't just been about collecting data, it's also been a test of endurance. Over time, Curiosity has aged, both in hardware and software. Its wheels have worn down, some of its cameras have been coated in dust, and the motors in its robotic arm have occasionally needed to be restarted. Even so, the mission team has kept the rover operational by constantly updating its software and reconfiguring its control systems. As a result, Curiosity has traveled over 18 miles and transmitted more than 900,000 images to date. But curiosity isn't alone in making strange discoveries. Over the years, many unexplained materials have been recorded on the Martian surface. Some were structurally odd, others were chemically unusual, but all of them raise the same central question for scientists. How did this form here? For instance, in 2014, Curiosity detected a mineral called tridymite in a region known as Cumberland. What made this surprising was its unusually pure silicate structure. On Earth, tridymite typically forms in volcanic environments and requires extremely high temperatures. But no such high-temperature volcanic systems are known to exist on Mars. In other words, this mineral was one of those things that simply shouldn't have been there. Another example was found inside a rock called Highfield, which showed traces of manganese oxide. This compound can only remain stable in environments with abundant oxygen. But as far as we know, the Martian atmosphere doesn't contain nearly that much oxygen. That's why the presence of this material on the surface is still debated. Either the planet's atmosphere was once very different, or these compounds were formed through some highly specific and still uncertain process. In addition, minerals like kaolinite, spinel, and pure silica, found in various regions of Mars, have also drawn attention. On Earth, the formation of such minerals is typically associated with long-term interaction between hot water and rocks. So these substances are significant not just for their mineral composition, but also as indirect evidence that liquid water may have once existed on the planet. But perhaps one of the most intriguing discoveries came in 2023, when Curiosity spotted bright white spots in a region known as the sulfate-bearing unit. In the images, these spots stood out sharply against the surrounding dust. Early analyses suggested that they might be composed of highly pure salt or perchlorate minerals. However, later data indicated that these formations may have crystallized near the surface after a sudden evaporation event or rapid loss of moisture. This raises the possibility that, at least briefly, liquid water may have been present on Mars in the recent past. Other exploration vehicles sent to Mars have also detected traces of materials that shouldn't be there, though in different ways. While these findings have occurred in geographically independent regions, they reveal certain recurring patterns. Traces of liquid water, chemical imbalances, and compounds that resemble byproducts of biological processes tend to appear as common themes in the observations of all three rovers. In 2004, the Spirit rover landed on Mars and detected an unusual mineral at a location called Home Plate, which at first appeared to be an ordinary geological formation. That mineral was pure silica. On Earth, this compound is typically found around hot springs or within hydrothermal systems. The fact that Spirit discovered it in a distinct and isolated area suggested that the region may have once been in contact with heated liquids. During the same mission, Spirit also identified carbonate-containing rocks. This discovery stands as one of the most direct indicators of long-term interaction with liquid water in Mars's history. Opportunity, on the other hand, traveled nearly 28 miles during its mission. One of its most striking findings was a group of small, blue-gray spherical rocks known as hematite spheres. Scientists compared these formations to iron oxide blueberries found on Earth in certain aqueous environments. When evaluated alongside the surrounding sediment layers, the presence of these minerals became one of the strongest pieces of evidence that liquid water once existed on the Martian surface. Perseverance, which began its mission in 2021, detected traces of organic molecules during its analyses in Jezero crater. These molecules are carbon-based chemical building blocks and are considered precursors to life. Notably, during sample collection efforts in two regions called Maaz and Seta, these compounds were found in the significant concentrations. Perseverance also identified minerals within layered formations, believed to be the remains of an ancient lakebed, that bore signs of water-driven sedimentation. Although these three rovers operated during different periods and in different locations, they all point to the same central theme. Mars was not always a cold and barren world. There may have been lakes on its surface, and perhaps around those lakes there were hot springs, mineral-rich deposits in regions shaped by active chemical reactions. But these similarities are not limited to the presence of water. Some of the discovered substances, carbonates, sulfates, manganese oxides, are compounds that on Earth are directly linked to biological processes. How they formed on Mars remains unexplained, because these substances are not only physically complex, but also the product of intricate chemical processes. And some of those processes are associated with cycles that may include the presence of life. But the answers may not be far away, because preparations are nearly complete for the first rock samples to be brought back from Mars. The Mars Sample Return mission, led by NASA and the European Space Agency, will be the first to physically transport material from Mars to Earth. It's scheduled to arrive in the early 2030s. The goal of this mission is to deliver sterilized and sealed rock and soil specimens from the Martian surface to Earth-based laboratories. That way, Mars's chemistry can be studied not just through the limited sensors of robotic vehicles, but with multi-billion-dollar analytical systems on Earth. Anomalous materials like the pure sulfur crystals Curiosity accidentally discovered in 2024 could finally be tested in detail under controlled conditions. This would allow scientists to examine the sulfur's purity, formation temperature, isotopic structure, and any potential microtraces at a microscopic level. Perhaps within these crystals lie the remnants of an ancient chemical cycle or signs of a long-past environmental shift. And that could be the starting point, because these crystals might be whispering a much larger story hidden in the silence of Mars.